we're able to create at micron scales, of tens of microns, these metamaterials. We can control them in real time digitally as fast as you can send a digital signal. We can deform these programmable fabrics. These piezoelectrics that we use as actuators in our technology are essentially instantaneous from a hardware perspective.
Can we give robots the ability to feel and touch just like we do, or allow ourselves to touch something halfway across the world? Hello and welcome to TechFirst. My name is John Koetsier. We've digitized sound, we've digitized light, but touch, maybe the most human of senses, has stayed pretty stubbornly analog. Maybe that's about to change. There's a new startup. It's building on tech from Berkeley and Virginia Tech. It's building programmable fabrics that replicate key mechanoreceptor functions in human fingertips, which could allow you or a robot the ability to experience in real time what a remotely operated vehicle, a surgical tool, a robot, or other user is touching. The same resolution as the nerve endings in our fingertips. Pretty wow. Impressive, if true. To chat, we have the CEO of Sensetics. His name is Adam Hopkins. He's a serial entrepreneur, inventor, and author. Welcome, Adam.
Hi, John. Nice to be with you here today.
Super pumped to have you. Tell us about this magical technology.
Yeah, absolutely. So as you explained, Sensetics is technology, is able to capture touch realistically at resolutions that exceed that of the nerve endings in our fingertips, and take that data, digitize it. And we don't have digital data for touch yet. There's a standard digitized format for touch data.
Yeah.
Create that and also play it back, all with the same type of technology, so that you can, for example, I could touch something here and you could experience what I'm touching realistically where you are, half a thousand miles apart.
Wow. Uh, Dive in a little deeper to that. How does that work? I mean, more sensors than on our fingers. We have like 3,000 per fingertip. That's insane density. How are you sensing that? And then how are you, the file format is kind of wild, right? It's not a JPEG, right? And then
That's right.
how do I feel it? Do I wear a pair of gloves? Tell us about the whole thing.
Yeah, so absolutely. So with respect to how many sensors, we have a capability, and this is some of the technology that came out of UC Berkeley and Virginia Tech that my co-founder, Ren Zhang, who's a professor at UC Berkeley now and was a professor at Virginia Tech, came up with. We're able to create at micron scales, of tens of microns, these metamaterials, which are, you can think of like scaffolding as a baseline for them, but it's very finely tuned scaffolding where the struts go in exactly directions you want, and they're planes and curves and as you like. We can create them and put in actuators so that they move how we want them to move. And importantly, we can attach tiny little wires to them, which are also created. They're not actual wires, but they're created via this technology I mentioned a minute ago, so that we can control them in real time digitally as fast as you can send a digital signal. We can deform these programmable fabrics, which is what I've just described. And then this technology is great because not only can we do that, but it's also sensing. When you deform it, it creates an electrical signal that you receive and record and capture just as quickly.
Wow, this sounds like science fiction.
Yeah, yeah. I hope it does, but it's real. We can actually do it.
So tell us how real it is. You started a company, you've raised some money. We're going to talk about that. We're going to talk about your next steps as well. You've got it working in the lab, I'm guessing, is what's going on right now?
That's right. So Ren is, as I mentioned a few components here, and Ren has demonstrated over the past couple of years, and indeed he's been working on this for, he would say, his entire life. And I think that's fair, but he's demonstrated these capabilities in pairs or in singular attributes. So for example, he has touch sensors that we've now recreated. I'm here in Princeton, New Jersey, our lab at Princeton as well, but touch sensors that are arrays of many sensors, tens of sensors at this point, not quite 1,000 yet, but that capture touch at high resolution. We can do super array level resolution, a little bit better resolution than number of sensors. And he's also created these actuated devices, these fabrics, if you will, that can move quite a bit via digital activation. And so on his website, if I can take a second to explain, and this is what first attracted him to his technology in the first place, so that we paired up and decided to do this together. But he's got this great video of a robot, and it's about the size of your pinky nail here. And lots of people have. It's not even a microbot, right? Okay, it's a little robot, but it's completely mobile. It's Bluetooth wired, and it is actually made from a couple different materials, mainly piezoelectric. So it's stiff, it's hard, right? But and it's made in metamaterial format, so his piezoelectrics are placed on this scaffolding, like I described,
Yeah.
and he can make it run and can make it do a backflip. He can even make it emit a sound wave to detect something in front of it, respond to that, turn and dodge it. All this, in this little package. So, you know, so we're pretty far on the scientific side. I'll say it's
This
not science fiction anymore.
this sounds like programmable matter.
Yeah, a little bit. That might be a Star Trek term. I'm not sure if they
I
trademarked it.
don't know if it's a Star Trek term. It's just something that I'm thinking that, that's a matter that I can just deform, create different shapes with, make move without traditional motors.
That's right, and that's so we called it programmable fabric. But
Huh.
it is exactly the way you described it. That's right.
So this is incredible. And now we're going to get into what this unlocks for humans, for machines, for robots. And we're going to talk about why it matters as well. But I just want to dwell on the mind blowing here for a second because our fingertips, and I hinted at that before, are super sensitive, right? We can sense differences 400 microns in size. You've said you can do tens of microns, which is more sensitive than our fingertips. We can sense a force of 0.2 grams landing on us. That's like a mosquito landing on our skin or something like that. Vibration, we can sense from 5 to 400 hertz. We have those 3,000 receptors per fingertip that I talked about, and then others on other parts of your hands and stuff like that. And we send that data to our brains at about 1,000 bits per second, right? So you've got actually something mechanical that seems better than the biological, and that just doesn't happen in robotics.
Yeah, yeah, I appreciate that. It seems like you have a really good grasp of this too, by the way. So that's fantastic, and I love this stuff too. So that excites me. But yeah,
Cool.
but touch, it's really complicated, right? There's 7 different types that I've read about of mechanoreceptors and nerve endings in your fingertips. That's more complicated than vision, right? Vision,
Hmm.
we've got rods, we've got cones. You could argue we've got 3 different colors of cones. Okay, so maybe there's 4 types, but anyway, it's not 7. And that's a lot of information that's coming in. Vision, again, it's about 100, 120 hertz at best, and as you pointed out, we're at least 1,000 hertz for the human case, with detection levels about 300 hertz. And
Hmm.
our metamaterials, the great thing about these scaffoldings is we can emulate the different types of mechanoreceptors. So, your Pacinian corpuscles, which detect deep pressure like a fork prong, right? Part of our structure behaves, our scaffolding structure behaves like them, and then there are
Hmm.
other structures that are very fine, like a nerve ending. So they're most of the 3,000, I think. They're part of our structure that behaves more like them. So we basically emulated them. So I don't think we've done necessarily better than the human body, other than we've been able to increase the detection thresholds because we've got
Yeah.
computers, right? But
Yeah.
but other than that, we've done this mostly by emulating those mechanoreceptors at different size
Huh.
scales, and then being able to wire.
Huh. Super, super interesting. Let's talk about what this unlocks. I mean, obviously for humans, I could feel something that a robot or a machine is touching somewhere else. And that might be important if I'm doing super sensitive work, maybe in a nuclear reactor, or maybe somewhere where I can't access physically the top of a mountain or something like that. That might be critical. That might be important. For robots, I mean, we're seeing so much going on with robots these days, right? Humanoid robots all over the place. It's really important to know, am I lifting an egg, or is it a steel container, or is it a soft something, a pillow, or what is it? How much force should I apply? Will I break it if I apply more force, right? And touch is one of the key things that we use to understand that in our world. Talk about what this unlocks for humans, for machines, and for robots.
Yeah, absolutely. And we've got a great video demonstration we can provide with respect to a robot gripper and how it can react to shear forces as they occur in real time, right? And
Yeah.
computer vision is not that fast when you're trying to track too many objects too much precision. It's not that great at distance. We do have LiDAR, but again, it is what it is. And touch is that fast, right? These piezoelectrics that we use as actuators in our technology are essentially instantaneous from a hardware perspective.
Wow.
The only time that comes into their signaling is the compute time of processing the signals. So I'll talk a little bit more about that capability. And also about the bidirectionality. So if you're going to interact with a virtual world as a human, you also need to have very high precision contact if you're going to experience touch, right? In a simulation, medical training. So let's talk about maybe medical training before we talk about robotic surgery. One of those cases
Yeah.
where you need to control your robot very quickly from afar and very precisely, right? But from a commercial perspective, you want to start maybe with medical simulation, just for FDA and regulatory reasons, if none others. But it's how you enter the field. And in that case, this bidirectionality really plays a large role. Humans interacting with the virtual and feeling what they touch with high precision, virtually touch. Just as important as robots interacting with humans. And, if they're robots interacting with eggs or soft objects, pillows, and being able to manipulate them without destroying them. And again, the duality or bidirectionality that I think is really exciting.
Super, super cool. You hinted at, as we were prepping for this, that this is particularly important right now at this particular point in history. Talk about that.
Yeah, absolutely. So right now, I believe it's been realized by those who work with robots, mainly, that robots need a sense of touch. And it's for all the reasons we just discussed, right? I like to point out that, can you walk without your sense of touch, or are you just going to fall over, right?
Yeah.
It's even more important than you know. In addition to being more fundamental, and it developed earlier from an evolutionary perspective in sight and sound, it's very meaningful, right? And it's fast. It's faster than vision for even in humans in the way I just described. So we need it to interact with the physical world.
Yeah.
And great, AI has done a lot with computer vision and allowed us to analyze images and audio very rapidly. And I think it's been realized now, though, that it can't do everything, like I said, for the reasons that it's not as fast as touch and not as precise when it comes to needing to drive control loops for robots that are going to interact with objects, manipulate objects, hands-on processes, even walking. But physical actions in unstructured environments, I think now it's been fully realized, you do need a sense of touch. You do need something more than just visual. You need to bring that to the table, right? And then the same goes, and I'll reflect that over to the human side and say, when you're interacting with this huge amount of information that's out there in our digital world, right? It's growing exponentially, more and more all the time. How do you interact with that productively? And this is one of those ways right now. While I would have loved to have flown out to meet you, we're doing this virtually, right? But either way, we're recording it, and audio and visual. That's a productivity tool that's due to the digitization of a sense. But the third digital sense, touch, can add so much more in terms of productivity and interaction with information. And there are a few big companies that invest heavily in human-machine interaction, improving it. And a lot of it's in this area. How can you use your hands, which are faster than our eyes, right, to manipulate objects in maybe a 3D virtual environment, and in training and simulation, right? If you're going to train to operate, like medical training we talked about, or train to repair a jet engine. And there are a lot of companies that already have virtual trainings out there that include touch. They see that their information retention is increased roughly a factor of twofold over a VR training without touch. So touch is really intrinsic. And I think now is the time that we've realized it, and we have the computational power and some of the AI fast tools, compute fast tools, to address it and really start incorporating into our digital world.
It's super interesting. I can totally see it for the aircraft mechanic. Like, how much pressure do I exert here, right? Will I break it if I worry about that if I'm trying to fix something around my house. How much pressure do I put here? My wife said, be careful, don't break it, right? How do I know how much pressure? My son-in-law actually works at a medical VR company where they train surgeons how to do different surgeries, right? And so how do you know how hard to press or where really challenging? You mentioned that the sense of touch is really important to walking. Well, we've all seen the humanoid robots, how clunky they look when they're walking. I mean, they're amazing for our current level of technology, but they look pretty clunky. Real life story. I was crossing a very, very cold river in very early spring, still snow everywhere, a little bit of ice, and lost all the feeling sensation in my legs. And that's very dangerous because you don't know when you're hitting. So you have to basically stomp. When it hits something, then you know you've hit the bottom, right? And then you
Yeah.
sort of go across very, very, very clumsily, but super interesting. Okay, so you've got to scale up. Obviously, you need bigger sensors. You need to mass produce it, all that stuff. Do you see key challenges in that? Do you think that the hard work is done, or is there a lot of hard work left?
Yeah. By the way, that sounds like I hope that was a vacation and you weren't just,
It was a
lost.
vacation, yes, and didn't feel very vacationy.
Not at that point. Okay. But very adventurous. That sounds terrific from some perspective.
Yes.
But yeah, no, certainly lots of hard work left to do. The science, as I mentioned, is done. The engineering, the scaling, the productization, not just making sure we have precisely what our customers will need, but also just making sure we have durable products, reproducible capabilities, high yield in our production are very important. So there's always a lot of hard work to do at a young company and when launching a product. Been around the block a couple of times in the startup world. This is not my first CEO role or my first founder role, and it might have been five or six, high tech startups, even a couple of metamaterials I've worked for. But I do love that holistic aspect of it, of
Hmm.
bringing together the commercial side with the manufacturing side, the scale up, the people that get involved, finding what works best, and making sure it works. Most important. But yeah, there's a lot to do.
Cool. So, and this can change. You're young. You've raised a seed round. I think it's 1.75 million or something around that. What do you think your first markets will be?
Sure. And I think we called it a pre-seed, by the way, which
Ah,
gives it
okay.
slightly
Leaving room
better.
for the $10 million seed round. I get it. Okay. Got to reset my expectations here.
Yeah, yeah. And that defines when, I think the nomenclature and the semantics define more than anything when we expect to have our first product coming out. And the answer is
Gotcha.
sometime in early 2027 is a target. We'll have a developer's kit we hope to be available before then. And
Okay.
what are we doing now? We're putting all those components together. I mentioned they've all been demonstrated conclusively and with high precision in a lab. And over here, we got started with Sensetics late last year. We've built out this lab now in Princeton, where our job is to build these devices to make larger arrays that are reproducible signals, to build out the microelectronics and that like. Most of our technology for prototyping is 3D printing based because it's
Huh.
fast, small format, relatively inexpensive. When we scale up, we can look more to screen printing and other capabilities that allow us to do
Interesting.
these multi-material creations at microscopic scale, but do them fast and really inexpensively.
That's an interesting insight. You'll print your technology eventually, almost like you'd print a book or something like that, but multiple layers, I'm assuming.
Yeah, yeah. There's some design constraints that aren't there in the more freeform 3D printing world, but
Mhm.
they're surmountable. We're thinking about it early. We
Cool.
want to use contract manufacturers to assemble our final products, but we want to produce, here in America, the core technology and keep the core IP close. And the reason we do that is perhaps perhaps obvious, perhaps not, but we don't want to give it away. We have a lot of patents. We have patents pending as well as license, but we want to keep it close, keep the development in house so that we can
Yeah.
learn more about it
Yeah.
and improve it as it goes along. But we don't
Yeah.
want to reinvent the wheel. We don't want to divine our own microelectronics contracts for components with producers in Taiwan or wherever it may be. So
Sure.
there are things that
Sure.
other people can do better than us, and we'll utilize and leverage them.
So talk about those first markets that you think, first products that you think will come out with this technology. What are you targeting first?
Yeah, so our first bet is controllers for simulation purposes and for virtual interaction. And
Okay.
these come almost simultaneously with robotic controls. So, we have some demonstrated robotic control features at small scale already. Integrating them into a full package and with software to drive them is takes some time, but again, that's what we're working. So, but if you can imagine a virtual controller, what will it look like? Very, very small. Our
Hmm.
skin, if you are programmable fabrics, about a millimeter thick. It's embedded in silicone-like materials. We can control their durability by controlling their elastic properties and their viscoelastic properties quite precisely. So that's
Mm.
that's that's relatively easy. It goes hand in hand with the tech, which is nice. So if you need to put this on a robot that's going to lift a table or a car, you can do that. You just need to
Huh.
embed a little bit more material around it.
Yeah.
And if you need to put it on something extremely sensitive, like say something that's going to go into the body and can allow a doctor to palpate your insides without actually opening you up, then which is fantastic, right? A great application that opens up something beyond robotic surgery. We'll get there, right?
Yeah.
It's ways
Yeah.
away. We'll get there. Then you can do that, and you can embed in a different material for that.
Super interesting. You mentioned durability earlier, and now you've hit on it again. And that's a real problem, of course, in robotics with hands, right? I mean, like you can make grippers, you can make all kinds of different. I think there's 1,000 types of grippers that Schunk, the robotics and engineering company out of Germany and Northern Europe, makes. And but if you're going to make something that looks like fingers, how do you make something that's also strong and durable? I mean, we solve that by regeneration, right?
That's right.
Robots don't have that yet.
When you were talking about how we could do something better than humans, I was thinking, well, we can't grow and regenerate them.
Yes.
We're not there
Yes.
yet, but
Yeah.
give it to them.
Yeah, this is super cool technology. I'm quite excited, and super interesting. And I'm a little surprised, kind of shocked about your projection for when you'll have a product in the market. Of course, I know those things change and reality hits and other things go on, but 2027 is not that far away. So that's actually quite impressive. Obviously, when people think about sense and touch, other uses come to mind. I have to ask about that. There's the whole porn industry, VR, and all that stuff. People are going to be asking for that. We see humanoid robots that have certain features that are coming out as well. I'm presuming that's not on your first on your list of your markets.
No, I can't say you're the first person to mention that either. So if you think about this long enough, maybe that comes to mind. But I'll suggest another application that might be a little bit actually in our flight path here, and that would be online sales of fabrics, right? How much time do people spend online buying clothes? And how
Huh.
great would it be to touch them and actually feel them? And that's not even that far away for us. That's not that hard for us to do. And with
Cool.
our manufacturing methods, like we're making something very small and thin at a
Yeah.
fundamental level. That's great. Size does cost more money. We're not
Yeah.
putting 16 kilos of metal into this or something of that regard. There's no engine that drives this with a lot of moving parts. It's matter that you shock, right? And it moves. I mean, that's it.
Yeah.
So fundamentally, this is not an extremely high cost technology or even a high cost tech. So I think those types of applications can come. They may not be first down the line because the first products may not be something that a consumer wants to pay more than 50 or $100 for. I'm not exactly sure how
Hmm.
much you pay to be able to touch the
Hmm.
shirt that you're about to buy. Some people would pay a lot, some would pay less.
Yeah.
But yeah, but with regard to that, I think those applications are again in our flight path and at some point in the future.
It's fascinating to think about. I mean, if you think about a computing device these days, and there's various different form factors without, but the one that we do most of our work on probably is still a laptop. And we think, okay, you've got a mouse, you probably have a keyboard as well. You've got a few other things and components around there, and some peripherals. And will it someday be normal to have a touch peripheral, a sense peripheral, where you can feel something like that? I mean, certainly when I buy clothes, that matters to me significantly, right? And also, we have significant technology these days for like, okay, what would this look like on me? And it'll model it on my body, but what would it feel like on me? That's an important factor as well, right? So super interesting stuff. I really appreciate this time. So I'll take a time out here and I'll edit this out. Is there anything else that we've missed? Anything else that we need to hit? We didn't. Go ahead.
Yeah, sorry, go ahead.
No, go ahead.
Yeah, we have this outline, right?
Yeah.
And I know we didn't hit on the let's bash the competition part of it, which we don't necessarily have to do, because I actually think the competition's pretty cool, or I wouldn't have gotten into this industry.
Huh. I'll ask the question though, are you guys alone in this? Who else is making something like this? And you can go whichever direction you want to go.
Sure, absolutely.
Okay, cool. I guess maybe before we end, I'll ask this. There's usually multiple players in every industry. Who's your competition here? Do you see any other cool products out there?
Yeah, absolutely. So I think this industry is inherently cool, and it's one of the reasons I got into it to begin with. And and there's some cool competition out there. But I would say in comparison to what we're doing, it's quite different. For example, in the force sensing space, almost every other tech out there, even the tech that has, resolution of a few millimeters, which would be very good. There's only a few things out there that do that. They're either not that durable or don't have the range, right? They can't detect a feather all the way up to lifting a table the way we can, right, without breaking, most importantly. But also I'll add that on the haptic side, it tends to be very mechanical age technology. I don't want to call it steampunk, but sometimes it's
Mechanical
close.
Turk.
Yeah, absolutely. Right. So I'll draw an analogy here. So we've got audio visual, and if you think about the telegraph, in 1850, right, 1875 maybe. It's not the telegraph to what we're doing now, video conferencing, is not a bad analogy, for the pneumatics and the mechanical devices compared to digital touch that we're describing that we're starting to do at Sensetics. And so, the pneumatics and the voice coils, which I think was invented in the very end of the 1800s, right? And the off-axis rotating motors and all those things that produce haptics or surges today. That's just it's just way behind. So I think this technology is quite groundbreaking from that perspective, force sensing and even more so in haptics. And that's one of the ways we're going to be able to meet these needs to do what others have tried to do in the recent past with touch and haptics and not been able to do successfully. I think simply because they didn't have this tech yet. Maybe they didn't quite have the computational power that they needed, but really the failing was in the core tech in the sense.
Well, it's super impressive. I mean, like if you can apply a current to some matter and then deform it selectively as you choose, you have programmable matter there, and then you can do some amazing, incredible, wonderful things and transmit that. You mentioned the file type, right? That you're developing in order to be able to transmit that and make that something that I can feel and something that you can feel and somebody a thousand of us, a million of us can feel. The feel of a basketball as an NBA player starts to make his 3-point shot or something like that, right? I mean, so many different opportunities and applications here. Thank you so much for
Absolutely.
taking this time. Super interesting stuff.
Yeah, thanks likewise, John. Nice speaking.